All right, so let's start problem solving for chapter 17. Okay, so let's start with the question number 1. Okay, so what we are given here. So it says that we have uh, we have two parallel plates charged with positive and negative charge, and the potential difference between the positive charge and negative charge is 5,000 volt. Okay, so this is the potential difference, and we have a charged particle. So here the charged particle is an electron. Okay, so the negatively charged particle. Okay, so if you remember from the lecture, for the negatively charged particle, the higher potential energy is close to the negative plate. Okay, and the low potential energy at close to the positive plate. Okay, so if you release this electron, it will be automatically going in this direction without um, getting extra help. Okay, all right, so that's the information we are given. And the first one, it asks us to calculate the change in electric potential energy. And the second one is the kinetic energy. What is the kinetic energy? And third one is the speed of the electron, okay, as a result of this acceleration. Okay, so let's see how to solve this. So the first one, it asks us to calculate the change in potential energy. Okay, delta PE. Okay, so if you remember from the theory class, that delta PE is related to the potential difference somehow, right? So it is you can get potential energy from the definition of the potential difference. Okay, so the potential difference between B and A, the plate B and plate A, is the change in potential energy over the charge. Okay, so here the charge is the electron. Okay, so delta PE will be then is equal to Q0 V BA. Okay, so here you see all the quantities are scalar quantities. So when we have all the quantities are scalar, then we have to be explicitly put the sign of the quantities. For example, electron charge is negative, so we have to make sure that we put negative sign for the electron's charge. Okay, so in last chapter we learned that the electron charge is this negative 1.6 times 10 to the power minus 19 coulomb, and the potential difference between B and A is 5,000 volt. Okay, so the change in potential energy is equal to negative 8 times 10 to the power minus 16 joule. Okay, so this is first one. So now let's calculate that kinetic energy. Okay, so the next one is, what is the kinetic energy? So so it says that the electron is accelerated from rest. Okay, so that means at this point it was at rest. Okay, all right, now basically when it is at rest, the kinetic energy at this point is equal to 0. Okay, so basically what we have to know what is the kinetic energy at this point. Okay, now to solve this problem, we have to go back to physics 1, where we learn conservation of mechanical energy. Okay, conservation of mechanical energy tells us that kinetic energy the sum of kinetic energy and potential energy at any point are equal. So for this situation, we can write the conservation of kinetic and conservation of mechanical energy as this. Okay, and this is equal to 0 because the electron accelerated from rest. Okay, electron accelerated from rest means the speed is rest, so the kinetic speed is equal to 0, so the kinetic energy is equal to 0. Okay, so now the only kinetic energy we can have at this position, at position B. Okay, so what is that? So if I solve it for kinetic energy at position B, we get something like this. Okay, now this is not the change in potential energy. Change in potential energy is final potential energy minus initial potential energy. So it would be something like this. Right, because you see that when if the electron starts from position A, so the position A is its initial position, B is final position. So the change in kinetic change in the potential energy will be PEB minus PEA. So then we have a negative sign. So the kinetic energy at position B is equal to negative of the change in potential energy that we already calculated in problem number A. So if you substitute the value, you get the exactly same magnitude but with a positive sign. Okay, all right. Number C. Okay, so we have to calculate now the speed. Okay, so speed is easy to calculate if you know the kinetic energy, as the kinetic energy is related to the speed by this equation, right? So here we know the kinetic energy, so it is B. So we can calculate the kinetic energy at position B. So if I solve this equation for VB square, I get something like this: 2 times kinetic energy divided by the mass of the electron. Okay, so VB is basically square root of 2 times the kinetic energy at position B divided by the mass of the electron. Okay, so if I substitute all the values, it would be something like this. Okay, and the mass of the electron is also given in the question. It is 9.11 times 10 to the power minus 31 kilogram. Okay, so then plug all these values in your calculator. You should get something like this. Okay, all right, so we are done question number 1. The next one is this. Okay, so again we have two parallel plate charged with positive and negative charges, and the potential difference between these two plates is 50 volt. The separation between these two plate is 5 centimeter. Okay, so 50 volt and 5 centimeter, and we have to calculate the magnitude of the electric field. Okay, so this can be solved by using add formula. Okay, so one of the formula we learn is VBA equal to ED. Okay, because it is equal to ED, sometimes it's called add formula. So by solving this, we can get E. So E equal to VBA D. Okay, although there is a negative sign in lecture, In theory lecture, you probably see a negative sign, but here we are interested on the magnitude only. So it doesn't matter whether you put a negative sign or positive sign here. So let me just use a positive sign. Okay, and here you see that potential is a scalar quantity, E is a vector quantity, and displacement is also a vector quantity. So when there are mixture between scalar and vector quantity, it is not very important to use the negative sign, okay, because we can determine the direction later, okay, by using the concept. Okay, so here this is the equation to solve for the electric field. Okay, so now we already know VBA is 50 volt and D is 5 centimeter. 5 centimeter means 5 times 10 to the power minus 2, okay, in meter. So if you plug all these values in your calculator, you should get something like this: 1000 volt per meter. Okay, all right. Number 3. Okay, so here we have to calculate the potential, okay, potential V at point this, okay, from a positive charge whose value is 20 microcoulomb, and from a negative charge separately. So if I draw the situation, it would be something like this. Okay, so here is our charge. It could be, for A it is positive charge, for B it is a negative charge. Okay, and let's say this is the point which is 0.50 meter from the charge. So at this point we have to calculate what is the potential. Okay, so number A, potential for a point charge, okay, is equal to K Q R. Okay, so yeah, make sure you don't write R square. R square is for electric field, and here we are talking about the potential. Okay, so don't make confuse between the electric field and the potential. Okay, and here you see all the terms are scalar. Okay, so here it is very important to write the sign, explicit sign. For example, for positive charge it doesn't matter. For negative charge we have to explicitly put its negative sign. Okay, all right. So now K is the Coulomb's constant, which is 9 times 10 to the power 9 Newton meter square Coulomb square, and then Q is 20 microcoulomb, 20 times 10 to the power minus 6 coulomb, and R, the the distance is 0.50 meter. Okay, so if you plug all these values, you should get something like this: 3.6 times 10 to the power 5 volt. Okay, now number B is basically the same thing, KQR, but this time we have to be careful because now the charge is negative. Okay, so everything is very similar except this value, which should be negative 20 times 10 to the power minus 6 coulomb. Okay, and then the value will be negative 3.6 times 10 to the power 5 volt. Okay, all right, let's move on. Okay, so here we have to find the minimum work, okay, must be done by an external force. Okay, so here someone has to do some work. Okay, this work done is not by the electric field. Okay, so it is by some external force. So you have to calculate that external work And what is the situation? Situation is to bring a charge q, a small charge q, from a great distance to a 0.50 meter from a charge this. Okay, so if I draw this, it will be something like this. Let's say here we have the q, that big q, 20 microcoulomb charge. Okay, and it is positive, right? All right, now q is also positive, right? So because q and both q are positive, big q and small q are positive, you know that and because positive repel each other. Okay, if you put in a positive charge here, it will be automatically going in this direction because of the repulsion, right? But if you want to bring a positive charge in this direction, you have to do work, right? It's basically similar to pushing a spring, right? When you push a spring, you know, you have to do some work on the spring. So similarly, if you want to bring a positive charge close to the positive charge, you have to do work. Okay, so that work done we have to calculate. Okay, now the situation says that you start from from r equal to infinity. Okay, so for a long distance to, okay, so you are trying to bring a charge q from a long distance okay, to a distance here. Okay, and this distance is 0.500 meter. Okay, so you are trying to bring a charge that magnitude is 3 microcoulomb from infinity, r equal to infinity, to r equal to 0.500 meter. Okay, now to solve this, let's start with this information. So in lecture class, you see that the work done by the electric field is equal to negative change in potential energy. Okay, so this work is done by the electric field. Okay, but here we are doing work, some external force is doing work. So, and that work we have to know. Okay, so the rule is this: the external force, the work done by the external force, is equal to delta PE. Okay, so I mean, in the similar way, I mean, when we derive this equation in lecture class, you can show that if you do the external work, then the work done by the external work done by the external force Wx is equal to delta PE. Okay, all right. So then what is delta PE? So in the first equation, in the first problem, we already see that delta PE is equal to Q0 VBA. Okay, so here VBA is the potential difference and Q0. So Q0 here is basically Q, because we are trying to bring Q from a long distance to a distance of 0.500 meter from capital Q. Okay, so here our Q0 is basically Q and VBA is basically VBA. Okay, now what is VBA? VBA is VB minus VA. So final potential minus initial potential. Okay, so in this situation, this is the final position, right? And this is the initial position. Okay, so at this final position and at this initial position, there is already have some potential due to this charge, due to the 20 microcoulomb charge. Okay, so what is that charge? At this point, VB will be KQ. So here you see this is the capital Q. So the potential is due to the capital Q. Okay, and what is the distance here? R is equal to this. Okay, and for VA is very similar, but then R is equal to infinity. So infinity in the denominator means it's very small. Okay, so this value is equal to 0. Okay, so this equation is now very simple. K Q Q 0.500 meter. Okay, so this is basically the external force. Okay, now if I plug the values, I would get something like this. So in the denominator we have one term, and that is this, and here we have K is 9 times 10 to the power 9 Newton meter square coulomb square. Capital Q is 20 microcoulomb, small q is 3 microcoulomb. Okay, and then when you plug all these values in your calculator, you should get something like this. Okay, so the amount of work done we need to do is 1.08 joule. Okay, all right. Next, so here we have two charges, actually dipole, right? So Q1 is minus 50 microcoulomb, Q2 is plus 50 microcoulomb. So the same amount of charge, but opposite polarity are separated by some distance. So this is a dipole, and we have to calculate first the potential at point A and at point B. Okay, so when we have multiple charges, okay, multiple point charges, and if I want to know uh, what is the total potential at some point, we have to individually calculate the potential for each charge, and then we have to add them together. Okay, all right, so let's first calculate VA. Okay, and VA will be equal to V1 at position A plus V2 at position A. That means V1A means the potential due to charge Q1 at position A, and same thing for V2A. V2A means the potential due to charge Q2 at position A. Okay, so what are those? It will be something like this: K Q1 RA1 K Q2 RA2. Okay, so you can take K out, so it would be something like this. So what is K? K is 9 times 10 to the power 9 Newton meter square per coulomb square. What is Q1? Q1 is negative. So here, because all the quantities are scalar, okay, so you have to be explicitly use the negative sign. And what is the RA1? RA1 is this. Okay, the distance from charge Q1, okay, at point A. So it is 60 centimeters. So 60 centimeter means 60 times 10 to the power minus 2 meter. And what is Q2? Q2 is plus 50 microcoulomb. And then this is RA2, and that is 30 times 10 to the power minus 2 meter. So then it just plugging all these values in your calculator, and if you plug all these values correctly, you should get something like this: 7.5 times 10 to the power 5 volt. Okay, Similarly, we can calculate VB. VB is V1B plus V2B. Okay. Again, it will be K Q1 R B1. So let me take K out. Okay. So what is K? K is 9 times 10 to the power 9 Newton meter square Coulomb square. Q1 is minus 50 times 10 to the power minus 6 Coulomb. Okay, what is RB1? RB1 is 40 centimeter. Okay, so 40 times 10 to the power minus 2 meter plus Q2 is plus 50 times 10 to the power minus 6 Coulomb. And what is RB2? RB2 is this distance. Okay, and you see that this is 26, this is 26. So because this line is at the middle, okay, the separation, I mean the distance from Q2 to B will be exactly 40 centimeter. Okay, you can use the Pythagorean theorem to do that, but even you don't need to do that. So by symmetry you can determine. Okay, so that is 40 centimeter. So 40 times 10 to the power minus 2 meter. Okay, so now you see that first term is negative and second term is positive, and the magnitude is exactly the same. So they basically cancel each other. Okay, so this cancel this, so the value VB will be 0. Okay, so the answer is 0 volt. All right. So now number 6, which is about capacitance. Okay, so let's say we have a parallel plate capacitor. We have to calculate the capacitance. Okay, what are given? We are given the area. So this is the area, and we are given the separation. Okay, so we already learned this equation. Okay, and this is the equation you need here. So what is epsilon 0? Epsilon 0 is 8.85 times 10 to the power minus 12 Coulomb square, Newton square, meter square. Area, so area is 20 centimeter, so 20 times 10 to the power minus 2 meter times 3 centimeter, 3 times 10 to the power minus 2 meter, and the separation is 1 millimeter. 1 millimeter means 1 times 10 to the power minus 3 meter. Okay, so plug all these values in your calculator, you should get something like this: 5.3 times 10 to the power minus 11 farad. All right, so once we know the capacitance, then the next one is what is the charge. So now we have to calculate the charge if this capacitor is connected to 12-volt battery. Okay, so we have to calculate charge. We are already calculated the capacitance, and we are given the battery voltage. So the charge, if you remember from the theory, related to the voltage and the capacitance by this equation. Okay, so the charge will be 6.4 times 10 to the power minus 10 Coulomb. Okay, so C is the Coulomb. Here's a unit of charge. All right. Next, the magnitude of the electric field. Okay. So again, we are going to use the add formula, V equal to ED. This means E equal to V over D. So you already know V equal to 12 volt and D is 1 millimeter, right? The separation between two plates. So that is basically 12,000 volt per meter. Okay. So the electric field there will be 12,000 volt per meter. Okay. The last one. Now we have to estimate the area of the plates needed to achieve a capacitance. So given that capacitance is 1 farad and the gap is 10 micron. Okay. So if the gap is 10 micron, okay, and 10 micron means 10 to the power, 10 times 10 to the power minus 6 meters. So if the separation is very small, and if we want to know, if we want to have the capacitance which is equal to 1 farad, what is the area? Okay, so let's start from this equation and solve for A. So if I solve this for A, I get something like this. CD over epsilon 0. Okay, so here C is 1 farad, they already told us, and D is 10 micron. 10 micron means 10 times 10 to the power minus 6 meter. Okay, so here it says that 1 micron means 10 to the power minus 6 meter. So 10 micron means 10 times that. And epsilon 0, we already know that is equal to 8.85 times 10 to the power minus 12 coulomb square per Newton square, per Newton meter square. Okay, yeah, so here I per Newton meter square, yeah. So if I plug all those values in our calculator, we should get a very big number. Okay. Okay, so the area should be this big. Okay, and this is unphysical. It's a very large number. Okay, so it's about 1 square kilometer. Okay, and having a capacitance whose area is one square kilometer is very unphysical. Okay, that's why when you buy a capacitor, you will see that it's written at the order of picofarad or microfarad or nanofarad, something like this. Okay, all right, the last question again is about uh, capacitor. Okay, but here it is about the stored energy. Okay, so it says that a camera flash unit store energy, okay, in a okay, so this is the capacitance and this is the volt. Okay, so we are given the capacitance and the volt. Okay, and we have to calculate the how much energy is stored in question number A, and then we have to calculate the power output if the energy is released in 1 ms, means millisecond. Okay, all right, number A. So we want to know what is the stored energy, and stored energy, so remember that we derived 3 equations. Okay, now the equation that involves C and V was this, half C V square. Okay, so half C is this, and V is this. Okay, so when you plug all this together, you should get 36 joule. Okay, and then what is the power output? Power is the change in energy with respect to time, right? Or the work done with respect to time. So here the change in energy is basically the potential energy what we get here. So energy changed is this, and the time is 1 millisecond, and milli means 10 to the power minus 3 second. Okay, so if you plug this value correctly in your calculator, it should be 36,000, okay, joule per second, or 36,000 watts. Okay, and that is the answer. All right, so with this we are done this chapter's classwork problem, and next I'm going to start chapter 18. All right.